All right, so me and this microphone are having some trust issues, so I'm going to hold this in my hand so I can see if this light here continues to go off on me. Anyway, so we're trying to figure out conditions for a vector field being conservative, right? So what we've done so far, we can come up with a test to decide whether a vector field isn't conservative, right? So for a C1 vector field here, if we have that in the 2D case, if a vector field F is given by PQ and Py equals, if a vector field is given by PQ and the vector field is conservative, then this must be true, that Py equals Qx, okay? Now in R3, if we have a conservative vector field, then it must be true that the curl of that vector field is 0. All right? Well, that doesn't help us figure out whether a vector field is conservative. It helps us figure out whether a vector field isn't conservative, though, because if Py is not equal to Qx, then this certainly isn't conservative. And if the curl of F isn't 0, then the 3D vector field certainly isn't conservative. Well, how do we start figuring out, a test for whether a vector field is conservative? In other words, is it possible to maybe turn these around and say, if we have Py equals Qx, then it is conservative. Or if we have curl is 0, then it is conservative. When do we have those kinds of things? Well, it turns out we have to restrict to very special sorts of things. So let's talk about two definitions real quick. So a curve C is simple if it never crosses itself between its endpoints, right? And then we say a region D is simply connected if every simple closed curve in D only ever encloses points in D, right? Now, this is the easiest definition for the 2D case. In the 3D case, you actually replace it with can be filled in with, or you have to imagine it, can it be the boundary of something that only contains points in D? So we're not going to talk about simply connected for 3D, just 2D here, okay? All right, let me check this light one more time. Okay, we're still good. All right, so what does the simple and not simple stuff look like? So let's do a little chart here where we put kind of simple up here and closed over here. And let's make a chart where we say yes and no, yes and no. Right? So what is, the mix of all these guys? Right? Well, something that's simple and closed is something like this. It crosses itself and it closes up. A simple guy that isn't closed, oops, that wasn't supposed to jump like that, is something like this, right? It never crosses itself, but it also isn't closed because it never meets up. All right, now something that's closed and not simple, well, you can pick a very simple one, the figure 8. That crosses itself. It is closed because the two ends meet up, but it's not simple because it crosses itself. And then finally, something not simple or closed, well, something like that, for example. I mean, it doesn't have to be that ridiculous, but so it crosses itself and the endpoints don't meet up, right? So with those two things, we can actually state now a theorem. And we'll do that after getting rid of all this. Now we can actually state the theorem, which allows us to check, given a vector field, when is it conservative, right? So the theorem comes in two parts, a 2D and a 3D part. right? So if F equals PQ is C1 on an open, I can't spell right now, on an open, simply connected region D, then if Py equals Qx on D, then F is conservative. Ran out of space. Then F is conservative on D, right? So that's the 2D case, okay? The 3D case actually gets, if you want the full general one, it's actually quite a bit more challenging than this. But for our purposes here, we'll just say if F is C1 on all of R3, I guess also a better way to say that is instead of than, say and up here, right? So F is C1 on all of R3 and its curl is 0, then F is conservative. All right? That's what the reversal of that test from earlier ends up looking like. Right? So you can see we kind of have to stick on a whole bunch of assumptions in order to say that, yeah, if Py equals Qx or curl of F is 0, then it's conservative. Right? There's a lot of kind of assumptions we have to build into that now. So conservativeness isn't really an easy thing to see for vector fields. It can be quite challenging, right? And it comes from sort of a topological condition. If you're really interested in learning more about that, you can check out something called de Rham cohomology.